Okay, let's talk about the multiplication rule for probability. We talked about conditional probability, but just a little review. First of all, the notation, probability of B given A. So this line means given. So given that this has happened, what's the probability of B? So an example, this might be, hey, given that you're a smoker, what's the probability you'll get lung cancer, right? Or given that you own a red car, what's the probability that it gets stolen? Those are examples of conditional probabilities. Now, conditionals, this part here always narrows down the size of your sample space, so of how many things you're looking at. So a great example is this one here. We're going to grab two cards. First card's a king. Now that we go grab a second card, what's the probability it's a queen? Well, given the first card's a king, that changes things because there's now 51 cards in the deck rather than 52. So that narrows things down to 51 cards. But there's still 4 queens, so work it out. There you go. So there's a conditional probability. Now another example would be blood type. Here's some data about some blood type. And now what is probability of being type O given that you're negative? Well, if given negative, that means we know you're negative. So you have to be one of these people, and therefore one of these 65 total people. Now of those 65, 28 are negative. Therefore your probability is 28 over 65. All right. One more example. Here's some drug screening, and what's the probability you got a positive test given that you're an actual drug user, not Doug's user, drugs. All right. But anyhow, so if you're a drug user, you're one of these people up here, so that's a total of 50. Whoops, that should be 50. I was thinking of the answer, I think, when I typed that. That should be a 50 here. And out of those 50, not 45, or not 90, out of those 50, 45 tested positive. So 45 out of 50 is 90%. All right, so that's conditional. Now, this relates to how we calculate the next bit. Now, these are for and probabilities. So, again, think of this like, what is the probability a car out in the lot is a Ford and it's blue? Okay, that's an and problem. And means multiply. So you could have independent events, and if they're independent, one has no effect on the probability of the other. So for example, given A, well, A has no effect, so it doesn't matter. So this is just the same as the probability of B. In other words, this condition doesn't matter, okay, because they're independent of each other. Given B, well, again, they're independent of each other, so who cares if B happened? It's just simply still just probability of A. So that's what it technically means to be independent. But think of it as just one has no effect on the probability of the other. Now, dependent events, they do affect the probability of each other. So given A has happened, that affects the probability. So it's not equal to just B. B has been affected. It's not the same. And vice versa over here. So an example of this, now another thing though, dependence does not mean cause. It does not mean certainty. So an example of this could be smoking and lung cancer, like I mentioned earlier. I think it's safe to say there is a dependence there. In other words, it affects the probability. So if I knew you were a smoker, that would affect the probability of you getting lung cancer. In other words, if I had a non-smoker and a smoker, the smoker is going to have a higher chance of getting lung cancer. Now, does that mean they will get lung cancer? No, it's not a certainty. Biologically speaking, lots of studies might even go as far to say cause. Smoking can cause lung cancer, but you notice there's a key word, can cause lung cancer. It's not a certainty. So, because it's not certain to cause it, we don't go that far in statistics. We would just say they're dependent. One affects the probability of the other. All right? So, selecting a king and then not replacing it, and then selecting a queen. Well, if I didn't replace it, that changes how many cards are left the second time. So these would be dependent events. Toss a coin, roll a die. Well, one has no effect on the other. Whether this coin is heads or tails, that has no effect on what happens on the die. So these are independent events, right? Now, if they're dependent, and means multiply, you multiply and you do it in order. So if A is first, you put A first. But when you go to do B, you have to think of it, oh, it's B given A has already happened. Right? If they're independent, it doesn't matter. You just multiply down the line. So probability of A times probability of B. And there's nothing to worry about. So they're both multiplication, whether it's dependent or independent. It's just you got to be a little more careful if they're dependent. All right. And this independence idea, by the way, can be extended out multiple times as long as they're all independent. So a great example of that. We're going to go without replacement. And so if I do that, probability of a king and a queen, what's the probability of selecting a king and a queen? And when we say a king and a queen, we then mean in that order. So if that's how it's worded, we mean it in that order. So king first, then queen. So probability of king times probability of queen, given that a king has already been selected. Well, there's 4 kings out of 52. There's 4 queens, but now, because I've already grabbed this card, there's 51. Work that out. There you go. So 0.006. Okay. Now, what's the probability? Roll a die, toss a coin, and getting a heads and a 6. Well, they have no effect on each other. Just multiply them. Heads, 1/2. 6, 1/6. 1/2 times 1/6, 1/12. Boom, done. So independent events are really nice. So let's extend this out. The probability that a particular knee surgery is successful is 0.85. So find the probability that there are 3 successful surgeries. Well, each surgery is independent of the other, and so we could treat these as independent events. And so just multiply. So success and a success and a success, and means multiply. They're independent. Just multiply, multiply, multiply. Don't worry about it. So the probability that all 3 of them are successful is actually 0.614, so 61.4%. Okay, flipping a coin twice and getting 2 tails, that's independent. So 1/2 times 1/2, 0.25, you're good. Probability of a queen and a queen, 4 out of 52. We replaced it. The next queen is 4 out of 52. No problem there. So we got that one. Drawing 2 cards without replacement and getting 2 queens. Well, since we didn't replace it, first one's 4 out of 52, but because we still have that card, there's 51 cards now. And also because we already grabbed a queen, there's only 3 queens left now. So there's your probability there. And this is a dependent example. And another dependent example, classic problem, is the bag of marbles. So my bag is 5 red, 3 black, 2 white. What's the probability I draw 3 and all of them are black? So that's like saying a black and a black and a black. Well, the first black, there's 3 blacks out of 10, but now there's 1 less marble, also 1 less black in the bag, so 2 out of 9. And again, now there's 1 less marble again, and 1 less black, so 1 out of 8. Multiply that out, 0.0083. So pretty small chance of this happening. Okay. So let's finish it off. Let's do a little bit more counting, and that'll help us do a little bit more complex probability, perhaps, and that'll finish off the chapter. So one technique is the at least once technique. Well, what is the probability of at least once? Well, if something happens at least once, that means it happens once, twice, 3 times, 4 times, all the way up to whatever you're looking at. So the opposite of that is happening once, twice, 3 times, 4 times, 4 times, 5 times, 6 times, 7 times, right? The opposite is none. So the opposite of at least once is none, not happening. Which means we can use that opposites rule with probabilities. The probability of at least once is equal to 1 minus its opposite, which is none. So we can use this with independent probabilities. Whoops. And this only works with independent probabilities, though. So the probability that something occurs at least once in n trials can be calculated like this. So if it occurs once in at least once in n trials, the opposite of at least once is none. But if it's happening none, not at all, in n trials, that's like saying it does not happen, 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 does not happen n times. And you can do that because they're independent. So if it's independent, you can multiply, 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 multiply. Well, the shortcut for that, because these are all the same, is like saying the probability it does not happen to the nth power. And so this is a nice little shortcut formula for the at least once scenario. So let's look at this problem here. What is the probability of drawing at least one spade when drawing 6 cards with replacement? Now I have to say with replacement because then that makes this an independent scenario, which you must have. So the opposite of at least one spade is no spades. So that's like saying I get not a spade, not a spade, not a spade, not a spade. How many times? 6 times. So 1 minus that to the 6th power. Well, how many not spades are there? There's 39 cards that are not spades out of 52. And so to the 6th power. And so crank that out, get 0.822. So the probability of getting at least one spade is 82.2% if I were to do this with replacement. Another quick example. We have some DVDs. We sell them in lots of 50. And the defective rate is 0.5%. So by the way, 0.5% as a decimal is 0.005. So that many are defective. So therefore 0.995 are good. So what's the probability of getting at least one defective disc in that lot of 50? Well, the opposite of at least one defective is no defective. Or in other words, all of them are good. Well, what's the probability of being good? 0.995. And then you'd have that happen 50 times. And again, we're using the opposite rule. So crank that out, 0.222. So the probability that you have at least one defective disc is actually 22.2%. So you have a really good chance that you get at least one defective disc, if not more, right? So that's pretty powerful. Looking at it that way, this defective rate does not look so great. You might say, oh, only 0.5% defective, that's really good. Well, if you think of it like this, that's not so good. I have a really good chance of getting a defective disc in a lot of 50. All right, so we'll finish it off now with counting. Just a reminder of the multiplication principle. Let's say the state of California has 3 letters followed by 3 numbers. So 26 possibilities for the first letter, next letter, next letter, 10 possible digits, 0 through 9 for this digit, this digit, this digit. So the multiplication principle says, hey, crank that out, you get 17,576,000. All right, so that is the multiplication principle. Now, a shortcut that comes up a lot is this factorial. So this exclamation is called a factorial, and what that means is you multiply the numbers down to 1. So 5 factorial, for example, would be 5 times 4 times 3 times 2 times 1. Which works really nice in this example, because if I have 5 people and I want to line them up for a photo, how many ways can that be done? Well, this guy right here, he could be the first one in line, or actually we could have rearranged them to be second or third or fourth or fifth. Or another way to think about it, how many people could be in this spot? Well, there's 5 people. Well, once I pick one of them, now there's only 4 people left for this spot. Well, now once I pick that spot, there's only 3, now there's only 2, now there's only 1. So 5 times 4 times 3 times 2 times 1. Well, that can be shorthanded as 5 factorial. And there's a button in your calculator to do that. And if you type that out, you get 120. So there are 120 ways we can line these people up. So it's using the idea of the multiplication principle, but using this special notation to make it easier to compute. Now, by the way, you should have a button on your calculator for this. It's under math or under the PRB area, probability. If you're struggling with finding that, then you can talk to me sometime in class, and I can show you where that's at. But how can we use this? Well, let's say you're a NASCAR. 42 cars start a race. How many possible finishing orders are there? Well, there's 42 choices for first, then 41 for second, 43 for third, etc., etc., etc. So if you crank that out, that'd be 42 factorial, which is a really large number, 1.4 times 10 to the 51st power. Huge. So a huge number of possible finishing orders. Now, you could say, hey, wait a minute, I don't care about the exact order for the entire race, but how many ways could you have the top 5? Or maybe top 10? Or maybe top 20? Well, that gets a little more challenging. Because if it's top 5, I can't use the factorial, because the factorial goes all the way down to times 2 times 1 at the end, right? But top 5 could be computed as 42 times 41 times 40 times 39 times 38. And you would get that answer. But that's kind of a pain. You'd think there'd be an easier way to do that. And there is. It's called a permutation. So permutation is this. So the formula is n factorial over n minus r factorial. Don't use this formula. There's a button on your calculator. Again, if I'm on a big fancy TI, you hit math, you arrow over to PRB, and you'll see it under there. And the way you type that in is 42, grab that NPR button or key, and then hit enter, hit 5, and then hit enter, and it spits it out. On the smaller calculators, there's a PRB button somewhere probably on your calculator, and that's where you would find these. So actually NPR, NCR, and the factorial should all be under that PRB key on those smaller calculators. Now, when you do a permutation, order matters. Order matters because I'm putting these things in order, right? First place, second place, third place, fourth place. That's an order that matters. This person first in line, that person next in line, that next person next in line, right? That's order. Order matters. So permutations, order matters, which is a kind of a problem for me because when you go to use this thing on your locker, order matters. So it's not a combination, it's a permutation. Okay, order matters. And we'll actually talk about combinations in a little bit, but this thing is actually a permutation. So one example, you got 15 people on a committee, you want to select a president, vice president, and treasurer. Now, if this was done randomly, that order does matter though, because if Joe is selected, if Joe is president, that is different than if Joe is vice president. Or it's different if Sally is president or Sally is the treasurer. So there is an order, there is sort of like an arrangement here. So order matters, and it's a permutation. And so you would type that in as 15 NPR3, and your calculator will spit it out at 2730. Now here's another type of permutation. This is a special scenario. So this is when you need to arrange things, but some of them you cannot tell apart. So for example, take the letters of the word Mississippi. How many ways can you arrange those letters? Well, I can't tell this S apart from this S, right? So the order matters. Like if I have an S before an M or an M then an S, right? That order matters. But if I swap these two middle S's around, you couldn't tell. So that's where this formula comes in handy. So there are 11 total letters. So the top is 11 factorial. And then you divide out any repetitions. So these four S's, 1, 2, 3, 4, I cannot tell them apart. So 4 factorial for the S's. We're going to divide out 4 factorial for the I's. I cannot tell the I's apart. And then 2 factorial for the P's. I can't tell the P's apart. And so those repetitions that you can't tell apart, you put down here on the bottom. And so if I work that out, that's 34,650. So this is a kind of special type of permutation where there's repetitions involved. Okay? So these are ways just to help us count. Last but not least is combinations, real fast. This is the formula for it. Again, don't use the formula, use the button on your calculator. It's under the same place as the other ones. Now, this has a special notation though. We can write it as this, 12 NCR4, but we use parentheses and we write the top number over the bottom. And notice there's no fraction symbol though. So this is special notation for a combination. Now, in a combination, order does not matter. It's just, hey, was something picked or not? So 15 people in a class, how many ways can 4 of them be selected to work on a project? Well, who cares about the order? It doesn't matter who was picked first, second, third, or fourth. It just matters were you picked to be on the team. So that's a combination. Order doesn't matter. 15 choose 4, or you can write it with the special notation, but put that in your calculator, you get 1365. Same thing with a deck of cards. In cards, it doesn't really matter what cards you got first. It's just, is that card in your hand? So how many ways can you be dealt 5 cards from a deck of cards? Well, that's 52 NCR 5, and special notation like that if you want, but put that in your calculator, spits out that number there. Now, we can combine some things though, and this is how we want to finish up. So let's say the Senate has 47 Democrats, 52 Republicans, 1 independent. How many ways can you form a committee that contains 3 Democrats and 4 Republicans? 3 Democrats and 4 Republicans. And means multiply, if you will. Now, how many Democrats? 47. I need to choose 3. Who cares who was picked first, second, or third? And I have 52 Republicans. Choose 4 of them. Again, who cares who's picked first, second, third, or fourth? So these are combinations, and you multiply them, and there you go. So if this was done completely randomly, this could happen 4 billion some odd ways. Of course, we don't pick committees at random like this, but if it was done randomly, that's how many possibilities there could be. Now you can take this and put permutations and combinations together and help us do probabilities. But just as a quick summary, here's your formula for permutations, but again, don't use the formula. Use the button on your calculator. But the big thing, order matters. Combinations, order does not matter. Let's finish it up though. Let's put it together with probability. So same kind of scenario as before, but now we're going to pick a committee of 10. And now what is the probability? There's 3 Democrats, 6 Republicans, and 1 independent. So one way to think about it, 3 Democrats and 6 Republicans and 1 independent, and means multiply. And then how many Democrats? There are 47. I need 3. It's a combination because order doesn't matter. Who cares? Are they on the committee or are they not? 52 Republicans, pick 6. 1 independent, get that 1 independent. So that's how many ways to do that and get that exact breakdown. Now, how many total possibilities? Well, there are 100 senators. I need to pick 10 total, right? So it's always about the total on the bottom. 100 total people, pick 10 total on the committee. And so that's the bottom number. And so you could crank this all out with combinations and you get a probability of 0.019. So in other words, there's only a 1.9% chance that this exact combination happens if this is done randomly. So that's how you can take it one notch further and do a little bit more complex probabilities.